SI. He's a lecturer in distributed systems at the University of Leicester in the UK. And he's been working on a number of things, including quantum computing. We've started working together when you were at TU Wien, and looked at enabling workflows on quantum computing systems. And so we're very happy to have you here to talk about your current work and future outlook. Welcome, Vincenzo.
Okay, thank you very much for the introduction. So, hi everyone, I am Vincenzo De Maio, as Mario mentioned, and I'm going to discuss today about my recent research work, which focuses on the challenges and opportunities of hybrid quantum classical systems. First of all, I want to give you a small background of what I've been doing. I graduated in 2016 in the University of Innsbruck with a PhD on sustainable cloud computing. So this is my main background. After this, in the following 7 years, I've been a postdoc in the TU Wien, in the Technical University of Vienna, where I focus mostly on two things. I started working on the energy efficient computing continuum, meaning energy consumption and resource allocation in edge computing system, IoT, and cloud. And then after this, after looking into this, I had a excursion into hybrid quantum classical systems, which HPQC project and different other collaboration, including one with Professor Delman, which is the main reason why I'm here. And since 2025, I have actually a double affiliation as lecturer in distributed systems in the University of Leicester, UK, and as co-PI of the Alpaca project and I'm here as part of my Discover US scholarship. I'm visiting for this time in 3 weeks as part of the scholarship. The first question that you may have is what brings someone with this background in distributed systems and HPC and to work into hybrid quantum classical systems? Why suddenly, all of a sudden, start working something quantum computing? The reason is this one. Everybody knows it. This is the so-called. This is how the number of transistors, the empirical law, the Moore law, how the number of transistors and consequently the processing power increased in the last years. In the last years, and we saw that at some point the computational power that we can offer in these machines started to stagnate. At some point, basically, we couldn't further scale the capabilities of current machines. And I mean, the reason it's basically we just couldn't predict that thing would turn up in this way. I mean, we couldn't predict such a growth. And I mean, around this time, there was a guy called Bill Gates who said something like 16 megabytes of RAM will be enough for everything. And around this time, more or less, IBM said something like, we believe there is a market in the world for like 5 computers. I see already more than 5 in this room. So we just couldn't predict. We tried to increase and increase. There was approximately in this time, I remember every 6 months coming a new Intel processor with, let's say, more megahertz. We were still in the megahertz era. Now we are in the gigahertz. And so power, at some point, we started to continuously increase the number of the power of the CPUs. At some point, we realized we couldn't do more than this. So we started to look into different type of making different processors work together, and still we are struggling to scale the computing power. But on the same time, the application that we are developing, especially now with the rise of LLMs and so on, they just don't mind what we have. They are more and more resource hungry, and we cannot scale further with the computational power that we have in classical computing. And to make things even more complex, the data, like this is very common. This is what we could see in the last years. We see that the amount of data that is created worldwide, which keeps increasing, and this data needs to be analyzed, needs to be processed, needs to be stored, and meaning that we need more and more resources. The reason for this is, I mean, any of you has something like this probably at your or different type of devices on you. This is one of the reasons. So with the advent of these devices that generate data and needs to be processed and stored, this becomes a very serious problem. And again, this has a significant impact for us in our life, because as we can see from this data, the global data center industry is estimated to emit these tons of CO2 through 2030. So you see the problem. Computational power that computational requirement that keeps increasing. On the other side, the machines cannot scale with this, and we have, as a consequence, it's not only about our requirements, but also about the planet, what we are doing for it. And so, the reason that brings me to this topic is maybe it's time to rethink the way we do the computing. And this is this time to consider alternative, or so-called post-Moore forms of computing. And the reason, and this is what motivates my main area of research now. The idea is to work on so-called hybrid quantum classical systems. Basically, the quantum will act as a specialized accelerator within HPC systems, similar to what happens with GPU or FPGA or other things. But of course, when it comes to quantum, things become a bit more complex. But we will go through this later on. We dive now in the first part of the talk, but we want to understand exactly how these hybrid quantum classical systems work in practice, and what can we define, especially in terms of workflows running on these systems. This is the experience that stems from the HPQC project. It's a project where I've been co-PI in TUVin, financed by FFD. And it's a collaboration. It's an awesome collaboration between AQT and IBM. Those are hardware producers quantum hardware producers. Three main Austrian universities: JKU Linz, TUVin, and University of Innsbruck. And then MatTech. It's a company focused on logistic optimization. The idea was to define the first workflows, one of the first ecosystems that has HPC and quantum nodes. And we could do it because we have AQT and IBM. And this is what we did. We integrated using specific APIs, we could run hybrid computation in such a system. Like we have different APIs that allow execution on this hybrid setting. But what does it mean executing something on quantum hardware? This is the scenario that you have. Now we are in the era of noisy intermediate scale quantum architectures. And we have, so meaning that, as we mentioned, we need quantum will work as an accelerator here. Also for a simple reason. The data that we have are inherently classical. And we need ways to process. So this data will be present on the classical side and and before we can work them on the quantum side, we will need to prepare the state or encode this data into something that the quantum machine can understand. Then on the quantum machine, computation will happen. We will go through this more in detail later, and then we'll perform a measurement. Please note that the process is non-deterministic because of the way quantum machine works, meaning that this loop will need to happen specific time in order to get meaningful result out of this. And this requires to solve different problem. We need to translate, as I say, the classical input into a quantum state. This needs to be understood by the quantum machine in order so that we can do something with it. We need to define what to do into the machine by means of, as computer scientists, we are used to define stuff in high-level language, and we want to compile this in a high-level description of what we want to do. This is the common abstraction that you have. Basically, the computation is modeled as a circuit with different gates and with different type of gates, similar to what we know from architecture. Where we have Boolean gates. Those gates are quantum, and this is what we need to know for now. Of course, also please note this is just one of the abstractions. This is the circuit abstraction, and this is the most common one. But there are also other type of abstraction depending on the type of hardware. But this is the topic for maybe another talk, even too, maybe. And then we need to perform the error correction. The N here stands for noisy, meaning these machines are inherently unstable. So in order to do something with it, in order to use this data in a meaningful way, we need to apply some form of mitigation and error correction in order to do something useful with it. How will our execution stack work? We have a user that will develop his application, and in this application, using the same language, we will have a quantum and a classical part. This depends exactly on these. We will use the same language, but some part will go technically on the quantum, and the other part will go on the classical side. The compiler, based on the available hardware, will then decide where to put. Will define two versions of the same code. Or according to the task, the classical side and the quantum side. So we have different type of. We have in this point different version of the same code, and the execution with each of them will have different output that will need to be aggregated and consumed in different ways.
You're solving the same problem twice?
No, some part will be on the quantum, part will be on the classical. Like this will be clearer later, but we have quantum task and classical task, and that's we have different problem. There are different sources of overhead here that need to be addressed. The compilation. Again, this part needs to be translated into something that the machine can understand, and this is particularly tricky. As we will see, we have some. I will show some results on this later on. But first of all, the quantum machine doesn't really have a memory, meaning that when we want to develop something on it, this will need to be redeployed on the quantum machine. Of course, there are ways to mitigate this, but this is the main thing. Also, the quantum machines have the qubit. We have different. They are formed by there are these qubits that are interconnected between them, and due to hardware limitations, the qubits are not fully connected. Meaning that you need to adapt your circuit to something that the quantum in order that it will match the topology of the machine. It's for anyone familiar with it, is basically subgraph matching problem, and this is particularly tricky also because you cannot clone a qubit, so meaning you cannot really copy. So you will need to apply specific mechanism of routing to make non-adjacent qubit work better. The data encoding, this is particularly critical because a bad data encoding, as we will see later, can potentially kill any speedup. Because maybe you have an algorithm that provides an exponential speedup, but encoding your problem into an instance of this algorithm will probably take exponential time, and this can be clearly an issue. Then the execution, again, you need to be considered once the time to execute things on the quantum machine. The measurement needs to be performed different time and needs to be performed different time, and also this causes the collapse of the quantum state, meaning that we need to reproduce the computation at the time. And then the post-processing, meaning there are different. This is also a source of overhead. I mean, not only in terms of error correction and mitigation, but also for the type of computation that we execute. Because you will see some computation will be actually offloaded to the classical side. Let's see some result of this. We have a preliminary study on the overhead of quantum circuit compilation. We performed this empirical study as a part of my IBM quantum credit grant. And the idea was to investigate how the circuit that we want to execute will affect actually the compilation overhead. And you see what we noticed here that most of the overhead is actually focused on different passes. So the compilation process happens in different set of passes, which are described here. And what you could see is that most of the computation, most of the overhead of the compilation is actually concentrated in few passes. And the point is that the type of passes will change according to the circuit that we execute. So this allows us to identify possible source. For example, what we can do about it, where we can work in order to minimize the overhead there. And I mean, there is a more deeper discussion on it, on this paper, which actually was awarded by the Springer Nature Best Paper Award in the ISBL Sci conference. And this is a preliminary part of this empirical study that, and we are now working on improving it. Another source of overhead that we investigated is in the context of HPC enhanced shadow tomography. It's a collaboration with Yotka Lins and with Richard Kung, which is one of the main person working in shadow tomography. For people who are not working in quantum know very well what shadow tomography is. If you are not familiar with it, the idea is that we want to characterize different properties of large quantum states, and this requires collecting a huge number of measurements in order to have this characterization because of the cloning and instability of the problem. But there is a way to reduce the number of measurements, like having a logarithmic number of measurements, by applying a protocol called shadow tomography. The idea, we take simple randomized measurement and then we perform the post-processing of this measurement classically. There are different ways to do it. I mean, this is one of the way that we perform, and of course this will move the work on the classical side instead. But of course, this is not guaranteeing that it will be faster, because we need to do it in the right way. And again, we need to consider the imbalance in data rate between the quantum and the classical machine. The quantum machine is inherently lower at the moment than the quantum one, than the classical one. And this is something that we wanted to take into account, which brought us to the main idea of this work, which will be on arXiv soon. See, while we collect data of the quantum machine, or maybe we can do something on the HPC side and use this slack time in order to do something with it and potentially speed up the computation. So this is how we describe our quantum state. We will execute it on a quantum machine, and then we collect measurement at different rates, and this will be then offloaded to the HPC machine. This is the type of data that we have. We have those are different unitaries that we use to collect different outcomes, basically a string, and you can see it as a string. And we will use these different measurements, these different samples, to distribute it to different HPC machines. And then we aggregate the result in order to update estimates of different properties. What we are looking at is especially trace of higher order moments of the density matrix. I mean, this is what you need to know is that this is a powerful detector for entanglement. For entanglement, you want to basically identify the degree of entanglement of a quantum state, and these different quantities define how much a state is entangled. And once we do this processing, we will continue working on it, and so on and so on. This will happen during this time. And at some point, we will collect different data, and we will have the possibly accurate estimate of these properties. And this is again a collaboration with Richard Kuhn from Yotka Lins. And this is exactly the main application we have been working on in this scope. Now, what did we learn from HPQC? From having to integrate quantum and high-performance computing machines? We learn first that overhead, before you can have a quantum advantage, actually there is a system overhead that cannot be neglected. We need to consider this, and because it can potentially kill any advantage. Because I mean, if you have to execute a specific quantum algorithm and it takes hours maybe to compile, then maybe it doesn't pay off. It is very important to adapt to the underlying system, depending on the type of machine that you have, what you have available. This can offer you different opportunities. The algorithm that you develop, they have to also adapt to the system constraints. Like in the sense that we have many algorithms, as we will see later, that make strong assumptions on the system. But in order to be deployed and to obtain something out of it, it is important that to adapt this algorithm to the system constraint. And actually, the classical HPC, if you don't do it properly, can be a bottleneck for you. Like you need not really mean, bottleneck is a bit too strong, but the idea is that it can, if you do not properly using HPC resources in this context, can actually not bring you any advantage. So we have different questions that we have different questions to address in order to do a proper execution. So what should go on quantum? What should go on classical? How can we adapt to the hardware that we have? And where does HPC fit in controlling all this? And this is what brought us to the work with Eva, the abstraction with the hybrid quantum classical workflows. The idea is, I mean, everybody of you knows the workflow represents an abstract computation. And I mean, I guess I don't have to explain it here in this room. But the thing is, so we have a classical workflow. The idea is to identify which part of this task can actually be executed on quantum according to the different algorithms that we have. Then we want to map this task into quantum task, maybe namely their implementations. Like we want to have these because there are possibly different implementation for the same algorithm. Because depending on because for example, if you have photonic machine, in this machine the circuit model doesn't work, but you will use another model that is called the one-way model or a measurement-based model. But again, this just to give an idea of what we have. There are different possibilities, and then we will need to add different nodes that will allow us to perform the decision at runtime. And if you are interested in knowing more about this was published in Future Generation Computer System and actually received the False Editor Choice Award in 2024. How does a decision node looks like? That's what we imagine. We have an hardware catalog with quantum and classical hardware and a repository of different quantum tasks. The idea is the monitoring layer will collect information about the available hardware, and based on this, the performance model, namely based on the data that we collect on the execution, we will decide what works better according to the available hardware. Is it the classical implementation? Is the quantum implementation? If so, if quantum, which one? And then if a specific condition is fulfilled, let's say we call it quantum condition, but this means if the quantum provides any advantage, then if not, it will go in the classical. If yes, we will go on the quantum task, of course, assuming data encoding and post-processing. These two sides will always be there, and we cannot ignore them.
How are you identifying, like, say you have a task, I give you a task. How do you know which route to take? I mean, what's your decision tree?
Currently, what you are doing is just that you specify manually where you want to execute. Because if you look at because identifying performance model, it's at the moment something they're still looking into. Okay. But the idea is more the proof of concept of how to do it. And based on this, we defined also a workflow definition language. I will go. This is I don't think this requires. The idea is to define the execution model and to focus on the visualization of the hybrid quantum classical system. We want to be able to perform the data in control, to control the data in control flow, defining parameters and output and the order conditions. And then the integration, meaning we need to be able to scale and extend the language. This brought us to the definition of Rigoletto, which is a spurious acronym for definition language for quantum classical scientific applications, and may be related to my deep love for opera, but this is something else. And then we focus on the expressivity of the language. We need to be able to express different different construct of hybrid quantum classical workflows. We need to enable interoperability between the classical and the quantum side. And then we need to ensure low redundancy. That's how the middleware will work. We have a user that uses Rigoletto and define his quantum and classical tasks, and then use Rigoletto to define the workflow structure. Based on the definition, it will come up with and it will decide where to execute. It will decide how this will work. And then the mapper will decide based on the decision node that we decide before, and also the available task and the information coming from the hardware catalog. It will decide where it will give this information to the orchestration layer, which will then communicate with the hybrid system and decide on this level where to execute, if on the classical, on the quantum, and then of course there will be some intercommunication between the two. This is again published into the CBI conference, and you can look into it later. And we have some use cases that we developed, starting from the molecular dynamics use case. We have we defined an hybrid quantum classical workflows of this application, and this is how we represent it. We have this is the only classical representation, and this will be the hybrid quantum classical representation. And again, this is described in more in detail in both these papers. But I mean, you are welcome. You are very welcome to check them out. What are the open issues in this moment? We need to consider the resource footprint. Like, for example, what does it mean? We are used as computer scientists and as HPC people to think in terms of resource consumption and how this application will consume resources. And we need to consider, for example, performance metrics. There are different performance metrics proposed by, for example, by IBM, the quantum volume or the circuit operation per second. And what we are interested in is how this translates into end-to-end execution time. We need to take into account the networking, because this is important for the data movement side. And another issue that recently has been started to pop up in the community is the energy consumption. This is not my work, but it was a very inspiring talk from Olivier Ezrati. And I took the slides are public, so I didn't steal from him, but at the end, so you can check them out. The idea is that you have people started to worry because the typical claim that you have in quantum computing is that it's energy efficient because it's reversible, which is to some extent true. The point is that you have so many other things that you have to consider practically. Like you have the cooling part, which is one of the main things, but also we have all type of hardware that has to be considered, and it's very important to consider each of these parts on the classical side, on the electronic of the quantum, and also the cooling and the vacuum pump. The benchmarking side, how can we actually compare across different platforms? How does a specific result working for superconducting qubit relate to for example, what is working on ion trap machine? And also how this work, for example, in different configuration between classical and quantum. Also, on the integration side, the different time scales that I mentioned. This is something that also we need to find a way to cope with it. And also, how does the control and the execution places in this? How do these affect the overall execution? And then we need to be capable to adapt to what we have available. And this requires the introduction of a feedback mechanism. Now, this ends the first part of the talk. Okay, so we saw exactly how this system work, and these are the systems that will, in the end, execute our applications and our algorithm. So we want basically, and this is one side of the coin. But now let's go on the other side of the coin, because why we want to use this application? We want to have a speed up. And how does it mean to have? What does it mean to have a speed up, first of all? And let's go on the near term. In the near term, like what can we do with the current quantum hardware? I mean, we have known speed up on different quantum algorithms. For example, the Grover algorithm will have a quadratic speed up on a structured search. Let's say while a linear search will go over big O of n, the Grover algorithm will take instead square root of n. The Shor's algorithm also guarantees an exponential speed up on polynomial factorization. The point is that these are not really actionable on speed up on current hardware. The reason is that the current hardware at the moment doesn't provide a few hundred of qubits, and most of these, in order to model a reasonable instance, you will require way more qubits than this. I mean, I think the biggest Shor's factorization was made on a polynomial that required 25 qubits. And the biggest RSA key, I think now the RSA keys are 2048 bit. So you see the difference in scale. Also, there is noise. Most of these algorithms assume that fault-tolerant quantum computers, and this is very critical. And then, of course, the overhead of the measurement. We need to perform the measurement different time and so on. Still, we have these devices. We want to do something with them. And what can we do with them? Recently, this paradigm called variational quantum algorithms has emerged. The idea is that because we wanted to something that can run using shallow circuits and doesn't require many qubits. So the idea is to represent a quantum state of interest via parameterized quantum circuits. You have the states that is parameterized with the vector of theta parameters, and you can see it as basic. I mean, go back to the circuit abstraction. Each of these U is a gate, which is a parameter, and parameter means imagine that imagine these as small spheres, and you apply rotations on different axes. This is the type of parameter we are talking about it. And we want to determine, then we encode the problem basically as similar to, as finding the ground state of a quantum system, basically the state with the lowest energy. And this will correspond to the optimal solution of the problem. So we want to identify we find representation of the problem, and we want to find the ground state of this quantum system. And we do this by optimizing classically. This is the key. We work on classical machines here, but we use the quantum to run our circuit, but then the optimization happens classically. And I want to minimize this cost function that identifies the distance between the ground state and the current state of the problem. And the idea, and we compute the cost function by measuring the expectation values of the system. So it's a statistical calculation. This paradigm is called variational quantum algorithm. That's how the scheme will work. We will have our problem here. This is a molecule because this is an idea coming from quantum chemistry. And we encode this molecule into a different into a different state. So this will go into the circuit as a state, and we will prepare the state and perform the measurement. Then we will perform we will check the results on this, and we will optimize in different iterations the theta parameters until we reach a specific termination condition. Those allow to execute stuff on near-term devices, and there are different pros and cons. The pros, we can exploit shallow circuit that can be efficiently implemented with current hardware, because the idea is that we implement circuits that are hardware efficient, meaning we can easily map them to the different different available hardware. Then it's because this it's relatively robust to incoherent and coherent noise, because those are shallow, and one of the main parameters affecting noise is the depth of the circuit, like how big is the circuit. So working with shallow circuit help us for the noise. The cons, though, is that we cannot really reach all the states if we use shallow circuits, and also the circuits are shallows, but then we need to perform more measurement, because as we saw before, this is an iterative process. So we will need to perform different measurement to collect our expectation. Then we perform the classical optimization, and we rerun all of this many times. So this is often a bottleneck.
But in other words, we don't know that the algorithm works at all.
Yes.
Right?
Another thing is also, and we focus on this is one of the first steps that we did actually was focusing on the tuning of HPQCs or variational quantum algorithms for execution of quantum machine learning calculations. So that's how it works. We have an initial theta, the execution on quantum, and then different condition. So and we have different type of parameters to consider. For example, which architecture we want to use, on which hardware we execute it, which cost function we select. This is particularly important for specific type of quantum machine learning calculation. Which optimizer, gradient free, gradient based, gradient free, which one? And then the termination condition of it. And this is a study that we performed together with Sabrina Herbst and Ivona Brandic, and it was published in the HPQC conference, and you can see more on it online. And other type of application that we focus on is optimization. I mean, we spoke basically, as you can see, this is an optimization. I mean, if you're familiar with simulated annealing, finding the ground state of a system, it's something that is very familiar to us. So we applied similar thing also in quantum optimization. Again, the problem here is though we have issues in encoding big instances of optimization problems. So it's particularly critical for us to encode meaningful instance on quantum problem, and we want to use them to perform optimization. So we applied exponential penalization, like a specific type of penalization for different instances, to beam packing and traveling salesperson problem, and we obtained quite encouraging result because the slack plus quadratic penalty is the standard approach that is used in. What we did, we applied exponential penalty, and we could see that we managed to use way less qubit, especially for the TSP. I mean, if you are interested in know more about this, again, this is part of this work that together with Measure Kanat-Bekova and Ivona Brandic.
Vincenzo, how did you know that you got the ground state? Like, you mentioned the condition.
Yeah.
How do you know that you can? What is the condition?
Actually, there is we cannot know. Actually, this is why what I forgot to mention is that the QAOA, that we focus on QAOA, and what we did is mostly focusing on we develop an approximate solution. Of course, we use the classical as oracle to compare the solution that we have with the quantum solution. But again, the solution is approximate, and you don't always get the optimal in this way. And we actually in the next slide this will be clearer. We don't really always reach the quantum state, the ground state, and the reason is that is basically all these because execution on quantum gives us access to this very huge hyperspace where we can look for our solution. But this comes with a caveat that is connected to the curse of dimensionality. People think the so-called problem of the so-called Barren plateau problem. The idea is that we have this huge space which allow us to explore and find potentially big solutions. Point is that we don't really know how to explore such a big space. And actually, the issue we have the gradient of our loss landscape. This will vanish exponentially in the number of qubit. Basically, what you have, you would like to have this. You go smoothly to the ground state, to the minimum. But what you get is more something like this. Your gradient is flat. You are not learning, and at some point you will stuck into a specific local optima, let's say. And to make you understand how the problem is particularly important in the community, 2023 I attended a workshop on quantum machine learning, and these are some of the papers that were presented on the topic. There is a very nice, I made a selection of them, but you can focus on if you are more interested to know about the problem, you can just read this very nice review of Martin LaRocca on Barren plateau operation on quantum computing. Me, what I like to do is to explain the issue is this meme that I like to show to my student when I talk about quantum machine learning. Basically, this is the life of a researcher in quantum machine learning trying to work with variational quantum algorithm. You think you find something, you end up into a Barren plateau. And starting from this study, we actually made our own hypothesis on this. Our hypothesis was that the issue of the trainability depends actually on the architecture that we use for their training. Because while on convolutional neural network or recurrent neural network, classical, we know exactly how they map to a specific problem, what each layer is doing and why. But here, what we do, we are instead adapting to the hardware that we have. So what do these architecture actually represent? So we focus our hypothesis was that the trainability issues are related to the architecture that we use. So we performed a study of the local neighborhood of the model space, defining a metric called channel sensitivity. It's a diamond norm between the neural, let's say, a perturbed version of the neural network. Let's say theta, the abstraction that you have. Those are the weights of the of a classical. You can see these as the weights of a classical neural network, and this is a perturbed weights of the neural network. So you have basically we calculate how we can distinguish the perturbed version with the non-perturbed version, And what we actually see is that for if you have a limited number of parameters, a limited number of qubits, you cannot really distinguish anything. So like we are basically not really learning something. We start to see a difference when we have more qubits. And again, not a very huge one. I invite you to check the scale here. So this is this is the type of distinguishability that we have. So the point is that it seems that to have some distinguishability, to actually start to see something in this level, you need to have more qubits. But we wanted to use variational because we don't have enough qubit. So this generates sort of contradiction. If you are interested in more about this was published in iClear 2025, and we performed in-depth characterization of this problem. And regarding, we also find an upper bound to the channel sensitivity based on the number of parameters that we have. It's basically a Taylor expansion of the channel sensitivity, and we see that the difference is basically grows in the size, the number of parameters, and in the number of parameters. It's a pretty loose bound, but it gives enough information, and that's how it grows. Again, more of this distinguishability can be observed when we have a higher number of qubits. And again, we see, but this was more or less expected because it's common also in classical neural network. Also, the change happened in the beginning of the training. Then at some point it will all flatten out. Of course, I mean, so we are doomed. There is Barren plateau. We cannot do anything. Actually, there are some architectures that don't have Barren plateau. You have, for example, quantum convolutional neural network. They don't have Barren plateau, or quantum generative models are also proved to be trained. But of course, there is a but. This solution basically trade expressivity for classical simulability. The idea is that models that are trainable, they don't have Barren plateau, but on the same side, they can be easily encoded as tensor network or on the lower rank circuits. Basically, what we mean, they don't have Barren plateau, but they are not very expressive, and this means they can be easily simulated classically. So the point is, if you can simulate them classically, why you need the quantum at all? On the other side, you have models that are present a high number of resources. For example, there are highly entangling, non-local, or problem-inspired. Those are very expressive model, but they concentrate. But in this case, we have Barren plateau, so because the gradient will concentrate around a specific point, and those are believed to be hard to simulate classically. And again, there is a question, very interesting question, again in this paper from the group of Los Alamos, Marco Cerezo, Martin Larocca, and Garcia Martin, and others. The idea is that what the question that there is maybe provable absence of Barren plateau actually imply classical simulability. And this is very important because basically it means that if you want to have an advantage of using quantum, you will need to focus on these ones, but then you have Barren plateau and you have to deal with it. So based on this, how do we look for our quantum advantage? Well, one of the possible ideas is taking a step back, like because what do quantum algorithms that have an exponential speedup in common? What you have, exponential speedup are commonly found in problems that have a very strong hidden algebraic structure. For example, short discrete logarithm or a Simon algorithm. These have very strong speedup, and they rely, mostly of them, on the building block of quantum Fourier sampling. I will not explain in detail what it is, but just to give you an idea of how it works, we have this Boolean function that will map from let's say of n bit will map into 0 and 1, and f is computable, meaning there will be a Boolean circuit that we can use to calculate it. This is the input, the circuit, and the result of the input. And we will show it with an example. We have this example. We have this function that is the inner product between of x with a secret string, and in modulo 2. And we want to find the secret string. How do we find it? If you have classical, we can do in this way. The x will give just 1 and all 0, and this will allow to find the first digit of u. Then we do like this to find the second digit, and so on and so on until we basically find all the digits. This requires at least n queries. But on quantum, I'm not gonna explain why, just because it will require to explain quantum gates and how they work. We need only one query to find you, assuming of course fault tolerant. This is how it will work. The idea is that we put in a superposition, then we encode this circuit into a unitary, and then we apply again Hadamard gate, and this will allow us to obtain U. This is the building block of many problems that actually guarantee a quantum speedup. We have an example. We have this unifying abstraction that appears very often. I'm not going to go in detail, but it's called hidden subgroup problem. We have an abelian group and the binary composition function, and we want to identify. We are given a subgroup, and we want to identify the subgroup given the set of coset and a function and the function that assigns label to each coset. The cosets are defined in this way. Basically, they are sort of switching of the shifting of the subgroup, and we want to identify the hidden subgroup through a certain number of calls to the oracle function. This is the type of structure that we are looking for, and this is application in different problems that guarantee an exponential speedup.
Why do you say guarantee? I mean, it's just that we don't know. We don't have a classical algorithm.
Yes.
Somebody could find one tomorrow, right? Yes. Or maybe they've already found it and they're not telling us. I mean, it could happen.
Yes, this is true, because actually there is no proven correlation between the complexity classes that we have here. But yes, that this is what in quantum will guarantee a speedup. But but again, the problem is encoding a problem in a way that we can then apply this subroutine and have our speedup. Other type of problem that we can guarantee technically speedup is in quantum is the problem called forrelation that's been codified by Scott Aronson in 2014. We have again a binary function that maps in this, and we want to estimate the forrelation, maybe the correlation between function f and the Fourier transform of G, and which is computed in this way. And we want to check whether these basically want to check how much these two are how much how the correlation between the two functions is. And this can be done in quantum using one query, while with bounded probability of error. While in classical we need this amount of queries. This is very cool. It can guarantee speedup, but again, it's a very artificial problem. Like it's designed explicitly to show that we can have a quantum speedup. And again, how do we practically embed this into an application? So what are the challenges in identifying speedup? From what we know now, the problem structure should have should be very easy to recognize. Like the problem structure must be then exact. Like we should have a very clear structure in the problem. On the other side, though, encoding could erase advantages, because again, maybe encoding these problem instances in something that is so complex could require could cause our execution time to skyrocket. Also, these different subroutines are extremely noise sensitive. They assume fault tolerance. Also, I mean, because it's based on the phase that we have, and if noise affects the phase, this will reduce the possibility to recognize the two things. On the other side, as similar to what actually to Itay said, classical baselines keep improving. So maybe we are running how to have something on this level, but when there is at some point maybe somewhere a classical baseline that can be already better. And then also we have to consider the benchmarking side, like how do we actually benchmark this optimization on current system. And going also on optimization, I mean we have algorithms based on Grover. They guarantee a quadratic speedup. We can have more than a quadratic speedup, but only for highly structured or very specifically designed tasks. You can you have some convex and semi-definite programming type relaxations that admit a better scaling than the best symmetric semi-definite programming solver, but only on certain instance families and assuming ideal hardware, and again, no ignoring the data movement cost. So there are solutions like QAOA that for the near term, where they provide some gains that are specific to instances in a different in runtime or approximation ratio, but against particular classical stacks and benchmarks, but not there is no global advantage. So it's very difficult to identify advantage in this context. What are the implications for us? I mean, what the possible idea would be that we could use quantum optimization as a specialized accelerator, like basically optimization will be a specialized function, a specialized kernel that can be used. But again, this will introduce orchestration and queuing overheads, and once these costs are included, which concrete workload would actually still admit super grover advantages? There is some effort in this direction. By this paper is called the intractable decathlon of quantum optimization. We have also researchers from IBM involved in it, and the idea is to find the idea of the paper is to identify 10 combinatorial optimization problems that in order to enable a systematic and fair benchmark of classical quantum and hybrid optimization methods, basically different instances that will be used to prove a speedup. And it provides standardized metrics and reported template. And the idea is to test common way to test quantum speedup claims under rigorous cost models. So that's how we imagine the general scheme to happen. And then our classical computation. Then at some point there will be a very specialized subroutine that will run on quantum, and then we will continue our execution to be on classical. So the speedup that we will have will be mostly local, so related to this specific subroutine and this specific part. And we need to the scheduling, the encoding, and the post-processing will dominate the cost. So how can we quantify our speedup? The advantage emerges only after the system costs are considered. So that this is what we expect from the time for classical execution. It will be the time for scheduling, meaning the orchestration and the decision and so on that is required, and then the time for, let's say, the best classical algorithm that you can, the best classical implementation that you can have. On the quantum side, you will have to consider the scheduling, but also the encoding time and the post-processing time, and then we will have the kernel execution. It's similar, but way more complex to what we have in the GPU, where if you are not careful, the time for encoding the data will can actually be your bottleneck. And this is the speed up that we can achieve a speed up only. This is how we will quantify, and this S will be higher than 1 only when we will take this into account. Taken all of these into account, the time for the quantum will still guarantee a huge speed up. Now we saw more or less what are the main challenges in this context. We will go through the conclusion of both on the system side and on the algorithm. So now let's go to the conclusions and exactly. So what do you think is more important, systems or algorithms? From my point of view, what we are dealing with is basically we are dealing with two sides of the same coin. In both cases, there is a lot to do. In the algorithm, we have assumption of structure of a specific instance. We have to consider the different circuit depth, which has, of course, an effect on the noise. You have the cost for measuring and the trainability issues and the noise sensitivity. So those are the issues that we have on the algorithm side. On the system side, we have problems with hardware topology that needs to be to which we need to map different algorithms. We need to reduce the compilation overhead in order to have something that is to have a meaningful speed up. Then the scheduling and the queuing overhead, the movement of the data, and again, energy and reliability. And if changing one side will actually affect the other as well. Because according to what the hardware can provide, we can perform different algorithms. On the other side, So the algorithm that we have define what the system should support, but also on the other side, the system that we have will define which algorithms are deployable in reality with the hardware that we have. So it's, in my opinion, the co-design of this, the co-design is the key to have any advantage in this area. And in the future, this is what we are working on. We focus on, the Alpaca project is focused specifically on quantum machine learning. The idea is to go away from the variational approach and focus on approaches that are capable of including inductive biases. Basically, one of the limitations of quantum machine learning is that the processing in quantum is inherently linear because those are unitary matrices. And what we have is that we want then to find ways to go to include nonlinear dynamics. And a way to do this is together with the University of Wien and the collaboration with Professor Philip Walter. They are experimental physicists working on photonics. They developed this device called quantum memory store. Basically, it's like a memory store, but it has different quantum properties. And these allow to introduce a sort of feedback loop that could possibly allow us to develop new learning paradigm with the classical and quantum. So the idea would be to introduce this into our hybrid quantum classical system and see whether we have some advantage. Now, what can we expect for the future in this area? What would be interesting to look for performance models for hybrid quantum classical systems. To consider this will be useful for orchestration and also for investigating the cost of data movement and also the energy consumption. I see this as a particularly interesting area. And then from theory to deployable algorithm, focusing again on the encoding, how we integrate them in the whole continuum and the whole benchmarks. And this ends my talk, but I want to take some time to thank the people who supported me in this year for my research. First of all, the Professor Ivona Brandic, which from TU Wien. She's the head of the research unit in computational sustainability there. And the PhD student with whom I work with. I mean, I still work with them, but mostly now with in this context. So, I mean, Sabrina Herbst, she's a PhD student working in quantum machine learning. Then Merjan Kanatbekova, she instead all the work on optimization that you is in this presentation comes from the work of Merjan Kanatbekova. And then instead, Felix Silk is focusing on the compilation side and basically on the, we call it quantum service computing, which is a very bad name if you ask me, but the idea is to integrate this in how to integrate the classical and the quantum side together. That's how, these are most of the work that you see couldn't be possible without the support of the student and the Brandic. Which brings me to the end of the presentation, and I'm happy to take your questions.
Let's be able to program quantum.
Yeah.
Well, you can already. There are different frameworks that allow this. The problem is that, for example, Qiskit, Pendylane, and basically each vendor has its own framework or if you want more specific control. The point is, what can you do with them more than how can you program them? Because for sure you can program.
I asked enough, I think.
Thank you so much.